I'm going to drive a Formula car upside down in a tunnel for 5 seconds through downforce alone. We've designed the car so our next mission was to find somewhere to complete this groundbreaking stunt. But where on earth do you do that? We thought surely there's a tunnel somewhere in the world that could be hired for this insane challenge. Well, this was way harder than we thought. So let me explain the surprising reason why we actually ended up designing our own tunnel. Now, my first port of call was to find someone who knew loads about tunnels. This is Andy Willis, a senior project manager in civil engineering, and he's in charge of our tunnel for Project Inversion. I set him off with the job of finding the right tunnel a while back, and it was difficult to say the least. So this is how we developed a bespoke tunnel in order to make this incredible challenge possible. First, let's start with traditional tunnels, of which there are 3 types. Tunnels that are being built for infrastructure projects, tunnels that are currently being used, like a car or train tunnel, or tunnels that are not being used at all, as they're decommissioned. And all of these types of tunnels have their problems. Tunnels that are being built are usually part of a massive and expensive infrastructure project where timelines are tight and budgets are huge. They're being built for a reason, and so are very unlikely to delay their finishing date at all for us to use and adapt their tunnel, just so we can perform a stunt, no matter how cool it is. Second are tunnels that are already being used. Aside from not being the right shape as they have a flat bottom, having an unsmooth surface and loads of electrics on the walls and ceilings, it would be very unlikely a government would close a piece of infrastructure for a month just for us. And thirdly, tunnels that are actually not being used. These would typically be older tunnels, which of course wouldn't be in great condition. And as Andy mentions, they have a bigger issue.
They're often made of concrete segments or brick if they're old. So the remedial works, or the works to modify that to make it suitable for the car so that you had a nice smooth surface so the aero wasn't disrupted, would be huge.
So after exploring these ready-built tunnel options, we quickly realised it wasn't the way forward. Not to mention the fact that with a normal tunnel, no one would be able to view the event live, and safety crews would have a difficult time getting to and away from any potential incidents. And really, normal tunnels just aren't built to the specification and tolerances that we require.
The thing that we focused on here was that we've got to be able to control the environment as much as possible. So Willem was very, very specific in terms of the aero requirements, and that is very, that's the absolute key to this, for the car to stick to the tunnel.
Imagine what driving down a bumpy road does to the aerodynamics of a race car, especially the downforce from the floor. Now imagine the consequences of this when that car is driving upside down. So we need to control the environment as much as we possibly can, and normal tunnels just don't cut it. The concrete segments are uneven and will have large gaps and bumps between each section. Between Andy and our aerodynamicist William.A, we decided the only way to keep the downforce consistent and to lower the chance of the car crashing was to build our own tunnel. So where do you start? Well, the first thing to decide was the diameter and the length of the tunnel. The length was relatively simple to figure out. Basically, how fast do we think the car will need to go to create enough downforce to drive upside down, plus 100% safety margin, multiplied by the time taken to transition to inversion and back, plus the time that we want to be upside down. And that ended up to be 700 meters. But the diameter of the tunnel is something different. First suggestion from Willem was 16 meters. That's 54 feet, or 2 London buses end to end. In other words, a very tall tunnel. And of course, the taller the tunnel, the more expensive this project is going to be. Now, Willem came back with 16 meters for a very good reason. He wanted to keep the gap between the car and the ground as small as possible. And the larger the diameter, the smaller this gap. A smaller gap means more downforce and less ride height change as we drive across and up the side of the tunnel. But after some discussion, Andy and Willem decided a 7.5 meter diameter was the best compromise. You could actually go a little bit tighter than this, but that leads to another problem, where the wheels are requiring too much camber to sit in the curvature of the tunnel properly. And so, with the basic dimensions decided, we needed a structural engineering company to design the tunnel in detail. So Andy went out to Expedition Engineering, who've designed some incredible buildings around the world. This project is going to be very expensive, and the structure is the biggest part of that. So Expedition have been focused on keeping the budget to a feasible level and making sure anything we do is sustainable and can be reused. And that was the really big challenge here, building a structure that could deal with the loads we were going to put on it. And so we hired a firm with a load of extremely experienced structural structural engineers to design something that is perfect for our application. They've calculated the load cases, worked with materials, and designed a structure that can more than deal with our use case. And all of these skills are founded in science, technology, engineering, and maths. And Brilliant.org is the place to begin learning these skills. Check this out, it's Brilliant's course on scientific thinking, and they have lessons based on structures. This is why Brilliant is great. It's a short lesson that you can do at lunch, on the train, or anywhere really, but that teaches you by doing, with engaging lessons that you can complete in your downtime. They have thousands of visual lessons from foundational and advanced maths to AI, data science, real engineering, and more, with new lessons added monthly. To try everything Brilliant has to offer, free for a full 30 days, visit brilliant.org/driver61 or click on the link in the description. The first 200 of you will get 20% off Brilliant's annual premium subscription. Thanks to Brilliant for sponsoring this video and the rest of this Project Inversion series. So it was decided to use temporary works, basically off-the-shelf components that are available to rent and can be reused, like a huge Meccano set.
With these sorts of off-the-shelf systems, you can get a very high degree of accuracy and consistency all the way down the tube, which is very important here.
So here's the structure design. Let me explain what's what. Starting at the bottom, the whole structure sits on concrete sleepers to ensure everything is level and true. We're using concrete sleepers so that we don't have to drill holes into the surface of wherever we do this, so we'll leave no damage. Off the back of the concrete sleepers, we have the tanks in yellow. These will be full of water and weigh about 10 tons per section, and these are to keep the entire structure in place, but also to help absorb some of the temperature, which I'll explain later, as this structure grows by 40 centimeters as the temperature changes, which also causes a whole host of problems. Then the red framework is what the structure is built around. It's called Vario kit, and they're off-the-shelf parts used for support when building bridges and buildings. This stuff is really like huge Meccano. Between the red C-shaped frames are the purlins. This is a subframe to give the road surface strength. And finally, the curved yellow surface is the road surface itself. This is in fact 4 layers of 7mm plywood that will be curved in a jig on site and then screwed into place layer by layer. That's the basic outline of the design that we've come up with. But how did the engineers get to this design? And how do they know that it's strong enough? The first thing to think about was the car and the unusual loads that it will put on the structure.
So when the car drives along, and it drives along with a suction in the order of about 4 kilonewtons a square metre, that's pretty much the same pressure on the cladding on the top of a very tall building.
Which surprisingly is something they're used to dealing with, as the air pressure on tall buildings is about the same. So that's why the road surface, the purlins, and the gap between the main frame is really important. Imagine this, you have the floor of the car sucking up the road surface, but you have the wings of the car pushing down on the tyres and into that same road surface. So the surface is actually being pushed and pulled and deformed in a really unusual way. And don't forget, we don't have an infinite budget for this project. We need to balance the strength of the structure with how much it's going to cost. So the spacing of the Vario kit and the purlins was important. An expedition decided that 9 meters of spacing was the right balance.
This is more like a bridge. You're spanning between stiff elements, and you've got to make sure the elements in between are equally stiff. And there's a further issue here, which is dynamics, because if you're going along driving along this and you're hitting every 9 meters this stiff hard point, then you've got a soft one and a hard point. Yeah. You've also got an impulse coming into the car, which we don't want either.
And that's a really important point. Race circuits just don't deform in this way, they're solid. But with a frame-based structure, if it's not strong enough, we could create a pulse going into the car, which could be disastrous. And that's not even the most surprising thing about this structure. Due to thermal movement, this structure could actually grow by 40 centimeters in a change of temperature.
If it's thermal movement of 30 degrees, so from the middle of the night to the middle of the day, which is quite a lot in the UK, but we normally design for more. If it saw a thermal shock of 30 degrees, the ends would move 200 millimeters outwards at each end.
And as you can imagine, if not designed correctly, that would cause a whole host of issues. And there's more. Steel actually thermally moves more than plywood, which would grow or sink by only 80 millimeters in those conditions. So you could have one part of the structure growing or shrinking by 5 times the amount of another part.
It's going to set up a whole bunch of internal stresses which you can't deal with. the forces are too high.
Now, this isn't actually a new problem. Materials grow and shrink when temperatures change, to varying degrees. You'll likely have seen expansion joints on bridges when you drive on and off them. These are usually foam or metal fingers between the main sections that expand. However, these bridge expansion joints would not work for Project Inversion. The foam would be too much of a bump in the surface and the fingers could affect downforce. So a bespoke design was needed here. Of course, the final location of the event will have a massive effect on how much expansion we'll experience, but we still don't know exactly where this event is going to take place. And if you're thinking that the plywood might not be strong enough if the car had a crash on it, you'd probably be right.
What we don't want is for it to penetrate the surface and then the car to plough into these steel frames at 9 meters centres, because we know what's going to happen if that happens. The car's going to stop.
As if the car was to go through the plywood and into a steel frame, it would stop very quickly, which isn't good.
Suddenly becoming stationary, that's what gets you.
So the solution is to add a steel plate between the plywood so it's not possible to penetrate it. And in the event of a crash, the car would slide along. Whilst this is still suboptimal, it's better than an instant stop. If you're a student aiming to work in motorsport, or if you already do, I'm looking for some help with something. So if you've enjoyed any of my videos, please help me out and take a look at the description and give me 2 minutes of your time. You can watch the full podcast with Andy and Sean just up here, and our other videos in the Project Inversion series just up here. Thank you very much for watching, and I'll see you in the next one.